Hi, everyone. As I was introduced, I'm Elad. I'm the VP of R&D for Redis Labs for the past couple of years. And I'm very proud to talk today about one of the most exciting technologies that we've implemented in the last few years, which essentially is the ability to replicate Redis across several geo-replication with our own technology, Redis Enterprise. What I'll try to cover today in the next 45 minutes is I'll speak about the challenges and the requirements behind this technology. I will describe very briefly our solution. Everyone that thought that they will come here and understand all the gory details behind this concept might become a bit disappointed, but you are welcome to come by and I'll try to elaborate as much as I can later. I'll speak about the Redis data types, several examples from how this concept will affect you as a user of Redis, and explain what is coming next as status and availability. Okay, so earlier today, I think Iftach and Ofer, our co-founders, spoke about doing more with Redis. A lot of customers come to us and say, look, you have a great product. We're using Redis. It's tremendous. It's working very fast, but now we are successful and would like to scale to lots of other geo-regions because we don't want to pay the penalty of latency between geo-regions in order to just use this tremendous product. So, such clients can be doing fraud detections. They might be doing real-time session management, metering applications, collaboration apps. All those, when become successfully, want to scale their data and the same data set across several geo-replication. The three base requirements that we got repeatedly from all our customers are the following. First, we'd like the same data set. We want it to be global. We want to use the same information on all the replicas, meaning I would like to be able to write and read the same information across all those geo-replication. The second, not surprising, we've all heard and learned to love Redis speed. We'd like to keep this speed capability even though we are scaling to multi-regions. And we have a working application. We don't want to change our application. We invested a lot of man-years into this implementation. We don't want to be required to change this application just because we made it now geo-replicated. So we got to work around 2 or 18 months ago, 2 years or 18 months ago. We started researching what do we have in the industry, and naturally we came across consensus, how consensus works. The application writes to one of the replicas, one of the clusters. In turn, this replica tries to communicate with at least the quorum replications. In this case, when we have 3, it needs to reconcile with one additional replica, gets reply that the information is indeed replicated, and only then it replies the application. As we spoke earlier, we know that Redis is very fast. Redis can support over 1 million ops per second with a latency of beneath 1 millisecond. But if you take into consideration the network latency, only between US East and West, the round-trip time is over 70 milliseconds. This can't work with Redis because if you worked this far with a very low latency and you want to scale your database, you don't adhere to the requirement that we spoke about Redis speed. So naturally, consensus since it requires cluster coordination, it's too slow to support Redis. But it doesn't end there. Consensus is based on the concept of last write win. The one that written the data last is the one that will eventually determine what will be the value. This doesn't work well with all of the complex data types that Redis provides. And in order to maintain the same capabilities, the client will need to change his application. coming back to the requirement that the client does not want to change his application. He invested a lot of time, and he doesn't want to change it. So we determined that this is insufficient, but what is? After some reading, we found out about a concept called CRDT, and the solution that we defined is called CRDB. CRDB, no surprise, is conflict-free resolved data types. It also can mean cross-region database, cluster-replicated database. You can decide what your favorite initials, but basically, behind the scene, everything means the same. It's a geo-replicated, strong, eventually consistent, CRDT-based Redis. Now, before I go on, just by show of hands, how many heard the word CRDT before today? Okay, how many are willing to come on stage, explain it? Okay, nice of you. At least one we have here. I'll try to cover a little bit about CRDT, but you won't get out of this lecture understanding all the mathematics and computer science behind it. First, because I don't know it as well. And second, because I don't think this is that important in the implementation. What I do want you to take out of this lecture is a bit about how we used it. So there are several building blocks behind this CRDB concept, and we start bottom up. First one is Redis replication. Redis replication has been with us forever, I think from the first version of Redis. It's based on master-slave model. Slave can be master for other slaves, and it supports high availability by changing roles, meaning one master failed, the slave can become the master, and when the master comes up again, it will be slave for that master. Based on that, 2 years ago, Redis Labs released a feature called Replica Off. Replica Off is basically like Redis replication, only it supports the ability to replication information between different regions across geo-replications. It supports the ability to use a compressed and secured replication link. It's optimized for one, and it enables you also, through the use of our architecture, to have different cluster topologies. Meaning, if you'd like to have a read replica somewhere else in an area that doesn't require the same traffic overhead as you had in another replica, you can have a different topology, a different number of nodes, different number of shards, and it can also support replication across several such regions, which means that if you look at it, you can understand that we already had, when we started, we had the backbone of having some kind of replication mechanism across geo replicas. Next is something that we've heard a lot over the last year. It's Redis modules. So Redis modules are with us very shortly with version 4 of the open source. It's running within the context of Redis, meaning that you can enjoy the performance of Redis when you implement new data types, commands, or capabilities. And this is used by us in order to provide some kind of a module that can manipulate Redis data types into new data types. What is the data types that we are trying to achieve? Any guess? Anyone? CRDTs, right. So, what are CRDTs? Things I don't understand. I guess we have a lot of common here between us. I don't understand all those buzzwords. Those are links. I will share this presentation at the end. You are welcome to press on it and to understand. I'm not sure even I'm able to pronounce some of those. Idempotence, I think I said it correctly. I'm not sure. I know what it means, or maybe I don't. Anyhow, I won't explain it. What I do want you to take from this presentation is as following. CRDTs are conflict-free replicated data types. They are researched in the academy for many years. They are just starting to be used in the industry in the last few months or so. It's based on consensus-free protocol, meaning I don't need to reconcile by communicating with other replicas, which provides us the ability to be strong, eventual, consistent. Strong eventual consistency means that I can do all my operation locally, and the synchronization is done without consensus. I don't need to communicate with other replicas to achieve this reconciliation. And it's built to resolve conflict and complex data types. There are proven structures that can support the Redis, specifically Redis data types, which makes it very easy to use with Redis. And it's mostly transparent to users. I say mostly because it might be affecting your application at some level. Not at the level that you'll need to use a different data types, but you need to understand how it affects or how this information might behave. So how do we reach strong eventual consistency with CRDTs? First, we are doing all our operations locally. You remember that we spoke about performance. So if I'm doing all my operations locally, I'm able to get Redis performance on my local replica. Asynchronously, I'm using the Replica off replication in order to communicate the changes, mainly the write activities, between the different replicas. And I reach the consistency using the CRDT model, which guarantees that the data set would converge regarding of the order. Some notes about it. First, partial inconsistency. Whenever you're using eventual consistency, strong eventual consistency, you need to take into consideration that for a short period of time, you might get different values from reads. This eventually will reconcile after all the replicas will communicate, and it depends on the network latency. So if you have a very slow network, it will take more time. Very fast network, it will take short time. Usually, from what we tested, it's about several tens of milliseconds that the data might not be aligned between them. The other thing to consider is we need the ability to identify when do we need to reconcile information. Because if every time that I get something from another replica, I will need to try to calculate and do the reconciliation within my replica, I'm wasting a lot of precious resources when I don't need it. In order to do so, we are using something called vector clock. Once again, show of hands, how many heard of vector clock? Okay, how many are willing to come on stage and explain it? Okay, good. I'll try. I don't promise that I'll be perfect with my explanation, but bear in mind that the concept behind vector clock is our ability to know if we need to do any reconciliation in our specific replica. So let's assume we have 3 replicas, and we'd like to know if events happen concurrently between them. I don't need to know if it was on the same millisecond or microsecond. I just need to know that it was done while the other replica was not aware of it. So we are all manipulating, imagine we are all manipulating the same key. So we start by replica A manipulating the key, writing some value to it, and we bump its vector clock to 1. At the same time, replica A didn't get any information from other replicas, thus their vector clock is 0. Then replica A replicates the information to B. B bumps up his vector clock to 1 and stating that he was aware of the change that happened on replica A. How does it do it? By saving on his side that replica A also sent him the vector clock of 1. Concurrently to that, or immediately after, replica B also update this key. And now we have B vector clock bumped to 2. And still, you know that if you look at replica B, it knows about the first update done on A and the second update done locally. Concurrently to that, imagine that replica C did 3 changes on the same key. So eventually we have the vector clock at C, which states that it had done 3 operations, but it wasn't aware of any operations it got from the other replicas. Eventually, this information is bumped to B, and now B is aware of the 3rd update done by C. it bumps its own vector clock to 3, meaning he reconciled this information, and while he did that, he was aware of the third update done by C and the first update done by A. Eventually, this information will be also sent to A, and now everyone is supposed to have the same value. This is, of course, will happen after B will communicate its information to C as well. How do we use it? In this case, if you look at here, you understand that Replica A didn't need to do any reconciliation because it's already known that B did this reconciliation within its replica, so we save precious resources, not needing to do any communication or any calculation on Replica A. And this helps us understand whether we need to do, whether we got concurrent activities from different replicas. I hope I've been managed to explain it better. If not, come back to me and I'll try to explain it afterwards. So, CRDB building blocks again. We started with Redis replication. Based on that, we are building Replica A for geo-cluster replication. Redis modules, which is used to implement internal CRDT engine that provides strong eventual consistency with vector clocks. So, all together now. First, we have local read and writes, where clients use regular Redis commands, meaning no changes on the application whatsoever when you're using CRDB. This information is manipulated internally in each Redis at the performance of Redis using the CRDT module. And then it's bidirectional replicated using a concept of replica of, we call it peer replication, and by that you achieve a kind of a CRDB database or a conflict-free resolved database that enables you to get the speed of Redis, not to require you any changes on your application level, and to be replicated across geo-regions. So, we've all saw the demo that Gian did earlier today, and I would like to take you a bit deeper into this demonstration and show not how easy it is to use it, but how easy it is to use CRDB to create such a database and start working. What is behind this demo? So we have one geo-distributed database. It's replicated across 3 clusters on US East, US West, and EU West. We have each Redis enterprise such cluster has integrated with it a web application that we've written, which runs memtir benchmark. How many heard of memtir benchmark? Show of hands. Okay, so this is something we use tremendously in Redis labs in order to test the performance of Redis. You can download it from GitHub. And to achieve the strong without consensus protocol eventual consistent, we have the peer replication that replicate the information between the different clusters, and we use the CRDTs behind the scene. So let's move for a short demo. What I'm doing now is I'll just show you the demonstration that you saw earlier today. So we have the 3 databases. I will just delete them just to show you how easy it is to recreate such databases. Hope it works. Okay, so I have now 3 clusters, each one you can see with 3 nodes and currently no database on it. The second one, same, 3 nodes, no database, 3 nodes, no database. So now what I will do is I will get into each of those clusters and I will check only one of them in order to get this database loaded. So I'm running a CLI command that we have to communicate internally between the clusters. This CLI command will communicate between all those clusters and will create this database. And if we will look now at each of those replicas, we'll see that there is a database already up and running here. Also, you can see here at the cluster manager, it's already syncing between running the peer replication behind the scene. And now what we need to do is we need to run this web server. So in order to do so, we have it, of course, ready before. And that's it. I have this demonstration running. Before I'll get into the demo itself, we'll just show you that I'm not running any memtier benchmark on any of those. And when I'll start creating the load, you will see the memtier benchmark running here. Okay, so let's start the CRDB demo just as you saw earlier today. So I'm starting by creating a load on one of those replicas. And you can see here that the US West one already has this memtier benchmark running. The other doesn't. As I will add the other two, you can see that we are reaching way beyond 3 million ops per second, the same latency as we had before. Let's make it show better so you can see it here. And now you can see everything is running over all those replicas. In the background, while this is running, we are running what Jian explained as a voting concept. We are running counters and set, and I'll explain a bit further how it behaves in the back. We are just emulating some kind of traffic that arrives into those those replicas. You can see that there are different values to each, but they are not very far. In the back, we have the async replication, which reconcile this information on the go. And of course, at any point in time, we might get different values. But if I will stop this traffic, just to show you, you can see, you can see that the data converged between all the different replicas. When I delete it, I don't delete it at all the replicas. I delete it only in one of them. And all of them reconciles and understand that the value needs to be deleted. So this is basically very simple to do using Redis Labs architecture to create a database, to manipulate it. All this information and all this demo will be available on GitHub after this convention. So you'll be able to test it and see that we are truly showing something here, and to even play with it. And I'll show later how you can join this kind of a preview. Okay, so this is about the demo. So what are the benefits that you get from using Redis Labs CRDB? First, as you saw, the performance are as fast as they were when you're running regular Redis. Not only that, if you add additional replicas, not only that you don't reduce your performance, you actually increase it, because each replica can serve the local traffic. So instead of getting 1 million ops, if you are using 2 replicas, you'll get 2 million ops with the same latency. Second, you can support different cluster topologies. This is very cost effective because as you scale your application, at first you might not have the same amount of traffic or for different geo-region. So you would like to start not with a full-scale cluster of 10 nodes, most expensive one is 100 shards. You might want to start with 3 nodes, maybe not as strong as the most expensive AWS instances, and to have only 10 shards on it and pay less for that. So you can have different topology. But not only that, you can also have different network topology. This is very important because one of the things that you pay for is a network bandwidth. So if you would like to be able to communicate on a consensus-based protocol, you will need to communicate with at least the quorum nodes. When working with CRDTs, you don't, because you can even have a ring just to close the network and be able to reduce the traffic that you are loading on your local cluster. Okay, so a bit about the data types. When speaking about the data types, I will try to explain it from the point of view of the user, not the point of view of the specific internals of how we implemented that. First, because there is some intellectual property behind it, and second, because I think we don't have enough time to explain all the gory details behind it, but I do want you to take from this example the understanding of how we are working with, or how working with CRDT will affect your application. So what is the example setup? We have two replicas. At each point, they are working on the same data set. Each step that I will show is done concurrently between the different replicas, and then some synchronization takes place behind the scene, and then we present the reconciled value on both of the replicas. So let's start. Let's start easy. You know what, I'm not sure it's easy, but let's start with counters. So Iftach, I think, in his presentation earlier today explained it a bit. Let's dig in a bit further. First, we are creating a counter. One thing that changes between creation of counters on CRDB comparing to before is that we can support change of data types. Meaning if you would like to have a counter, you need to start by incr by. You can't use set and then do incr by. But let's assume that Replica A took and increased my key, which is the counter, by 10. The result is 10. If you will try to read it, you will get 10. If on the same time you would like to read my key on Replica B, you will get nothing. Not surprising, because nothing was done and you haven't synced between the replicas yet. Then some synchronization is done in the background, and surprise, at the end, you get the same value on both of the replicas. That's easy. Let's assume that there are multiple value changes done concurrently between the two replicas. So we had the value 10 to the counter, and we increased it by 5 on Replica A, resulting with 15, and increased it by 8 on Replica B, resulting 18. Now this is supposed to explain the multi-value concept. The multi-value concept means that you can't just take the value from one of them and decide that this wins. Even if the incr by on Replica B was done after Replica A has increased the counter by 5, you can't just decide that this wins. This is not a last right win concept. You need something else. The way we implement it, we need to keep the information of each replica and to sum it up together. So after the synchronization, we will get 23. Even though you read in your application and increased it by 5, after some time, because some other user increased it by 8, you will get this value. Okay, so one of the most important concepts in CRDT is add wins, observed, removed. It's the same thing. Add wins, observed, removed refers to the same concept. If you remember vector clocks enables us to know what was a situation when we've done something. It means that if I'm removing something or changing something, I know what the other replicas had at the time that I did it. So what will happen in this case if I will delete my key on Replica A? Until I converge or until I do the synchronization, Replica A will think that there is nothing. If at the same time Replica B decreased my key, it will get 20. But after synchronization, anyone would care to guess what will be the value? 20? Any other suggestions? What? Okay, bear in mind that when Replica A did the delete, it knew about the value 23. So it actually deletes 23 from the values. At the same time, Replica B reduced additional 3. So the final result will be -3. You took the 23, and you took additional 3 from it, and this is why it got -3. Let's see if next in the presentation it will become more clear. I'm repeating the same concept over and over again. So, sets. Sets are implemented based on something called OR sets, not surprising, observed removed set. So how does it work? Let's assume Replica A adds X to a set, and then, of course, it reads it, and it gets X. And at the same time, Replica B also added the same value into my set, but also removed it. Now, you remember, once Replica B removed the value X, it wasn't aware that Replica A added. So even though for a certain amount of time it might get empty list, after the synchronization, it will still get X. Another example, now with a quiz for it. No prizes, I'm sorry. You know what? Whoever will guess right will get the preview version of Multi-Master. So I add Y to the same set, and Replica A thinks that I have Y and X. At the same time, I deleted my set, and it's empty on Replica B. After reconciliation, what do you think will be the value on both sides? Y. Okay, you got it. Good work, so it makes it becoming more easy. When it doesn't need to do any calculus behind the scene, it's very easy, right? Okay, so registers or strings. Strings are implemented using something called registers on CRDT. There's a lot of research behind it. You're welcome to read about it. The main difference between strings and the other data types is that it requires us to take into consideration time. This is the only situation that we need to take into account. And let's assume that Replica A sets my key as A and get it, of course. And slightly after, even though it's done concurrently, assume that we are synchronizing using NTP servers, and we know that the same time are on both replica. A bit afterwards, Replica B sets my key to be B. And after reconciliation, last write wins will mean that we will get B on both sides because B was written slightly after Replica A written A. Is it clear? Does it make sense? Every local clock, and if you don't have synchronization between the servers, you might get problems. So if you are communicating with an NTP servers and you are synced, then that's the clock. Add win observed removed. Once again, I delete my key on one side and set it on the other, and at the end, I will get surprising C. Okay, so with that, I would like to move to the status and availability. There are other data sets. You're welcome to come by and ask about the implementation. Hashes is implemented using sets with counters and strings. Sorted list is using sets and counters, and list is using something called diagonal acyclic graph, which basically is a linked list that you can add elements before or after specific entries, and you send which value you want to get after or before. What is the status and availability? So first, at Redis Labs, we have 4 types of products. 3 of them are, or all of them are based on the same architecture, but 3 of them are provided without the need to run multi-tenancy, which is Redis Cloud Private, which runs over the cloud and over your infrastructure, and we provide it with single-click bootstrapped. Redis Pack, which is on-prem solutions that you install on your servers, and Redis Pack Manage, which is the same as Redis Pack, only we provide some management capabilities for us to help you with the DevOps activities. All of those will be able to support CRDP. The only one that won't is Redis Cloud because it's a multi-tenant environment. And also, I don't think that someone that is using Redis Cloud will try to scale for geo regions. And if he would probably use Redis Cloud Private. The status is that we are very close to complete a preview version. Whoever would like to join this program is invited to contact us at pmgroup@redislab.com to enroll. It will be GA'd with the next version of Redis Pack coming shortly this year, and this will support the following data types. It will support strings, counters, sets, pub, sub, expiry, and hashes, and later on will support all the rest of the data types. So with that, I come to questions. Any questions? Really? Oh, okay.
Hi. When will this get rolled into Redis Search?
Implementing Redis modules with CRDB is planned not for the coming version, but the next one, and we will support the Redis Lab modules with this, including Redis Flash, Redis Search, Redis Machine Learning, JSON. All of those will be supporting on the next CRDB version.
And when is that?
Are you from sales? From Redis sales? Okay, so I believe that sometime next year.
Thank you.
With your different topologies that you support, you have full mesh and circle. Do you support tree structures so that you can...
We support any topologies that is able to communicate between, or to close a full loop.
Okay, thank you.
Any other questions? Amazing. I was thinking that it won't be clear and people will have a lot of questions. So you can use spare time to come by and ask anything if something isn't clear. And thank you for your time.